Hello! In this video, we are going to solve together the example provided in the previous video. So it is very important first to read carefully the question and determine what is given information for you and what is required to calculate. You can use also this tip when solving the exam questions. So let's read through part A. A three-phase synchronous generator with a synchronous reactance of 25 ohm is connected to a 10 kilovolt phase voltage grid and supplies 1 megawatt at a 0.819 lagging power factor at its terminals. Let's stop over here. So we have a three-phase synchronous generator. This parameter is XS, and this one over here is the per phase voltage, and we have the output real power, so this is the real power, okay, 1 mega, and then we do have the power factor, so this is cosine theta. Okay, what we need to calculate? So calculate the phase current and the resultant V or across XS, and from the phasor diagram graphically determine the required excitation voltage and the load angle. Now in part B, it says that if the load is increased to 3 megawatts, calculate the resultant changes to the phase current, the power factor, and the load angle for a constant excitation voltage. So let us start by calculating the parameters required in part A. We need to calculate the phase current. So in order to calculate the phase current, we need to make use of the information we have. So we have the power factor, and we have the phase voltage. So this is the lagging power factor. We know from the equation of the real power, it is equal to 3 times the magnitude of the phase voltage and the phase current and the power factor. So we already have the power magnitude or value, and we already have the voltage per phase. This is the variable that is missing. Everything else in the equation is known. So if we isolate the current per phase, we are going to get its magnitude, and we know the phase from the power factor that it is minus 35 degrees. Now this is the first requirement. Let's take a look. What was the second requirement? The second requirement was the resultant voltage across XS. Okay. Now, in order to do that, we already have the current value now. We already have X of S. So the drop of the voltage across XS is equal to the current times JX of S. So in this case, putting all the parameters together, we will get the magnitude of V across X of S as this value, volt. Okay. Now, in order to determine the excitation voltage, it is the phasor summation of the voltage per phase and the voltage across the inductance reactance. If we add the phasors, what we will get the magnitude of the excitation voltage. So missing here is the unit, volts, and the angle that we obtain over here is actually the load angle. So this is the load angle, and if you would like to see it in a phasor diagram, take a look over here. So now let's see what happens in part B. Okay, so in part B, the load is increased to 3 megawatts. We need to calculate the resultant changes to the phase current, the power factor, and the load angle when the excitation voltage is the same. So the excitation voltage is exactly the same as the one calculated in part A. So let's take a look at the solution over here. We know from the equation which relates the power to sine of the load voltage that it is equal to this formula. So we plug in the new value for the power, which is 3 megawatt. We keep everything the same, so X of S is the same, the excitation voltage is the same, and the voltage per phase is the same. So in this case, we will obtain the new load angle. So this is the first requirement done. The next requirement is we want to see the change of the phase current. So we can calculate the excitation, we can calculate the phase current from the excitation voltage equation. So now we keep everything the same, but now we will have a new value for the phase current. We plug in the parameters, and in this case we will get the new magnitude for the current as well as the new power factor. So in this case, if we have the angle of the current, we can get the new power factor as 0.95. And this ends the solution for this question.